Gate 2023 physical metallurgy questions. At 1 atmosphere, the alpha, the ferrite iron transforms to austenite iron above 912 degrees centigrade. Density of austenite is more than that of alpha ferrite. Choose the correct statement. Increasing the pressure above 1 atmospheric pressure lowers the alpha iron to gamma iron transformation temperatures. Is this true? Increasing the pressure above 1 atmosphere lowers the alpha ferrite to gamma ferrite transformation temperature. This is true. And increasing the pressure above 1 atmosphere raises the alpha to gamma austenite temperature. This is false. Molecular volume of gamma ferrite of iron is higher than molecular volume of alpha iron. This is not. The pressure change will not have any effect on the alpha iron to gamma iron transformation. This is also wrong. Now let's see each statement. The increasing pressure above 1 atmosphere lowers the alpha ferrite to gamma ferrite. This means this statement is generally true for all the substances that exhibit the phase change with pressure, because an increase in pressure tends to form a denser material than in case the denser material is austenite. And increasing the pressure above 1 atmosphere raises the alpha iron transformation to gamma iron. This is also not true. Increasing the pressure would favor the transformation to gamma austenite at lower temperature. Suppose if this is the gamma to alpha temperature, the temperature decreases to lower point compared to the previous. Okay. The molar volume of arsenite is higher than molar volume of alpha iron. The statement is not directly mentioned, but it's the common trend that when a substance undergo phase transformation to denser phase, its molar volume tends to decrease. Okay. The pressure change will not have any effect. This is incorrect, because the transformation of alpha to austenite is affected by pressure. At higher pressure favors the formation of denser phase. So the most accurate answer is A. Diamond has a low electrical conductivity, modulus of elasticity, hardness, and thermal conductivity. The diamond has lower electrical conductivity. It's not modulus of elasticity, hardness, or thermal conductivity, because the electrical conductivity, the diamond are excellent electrical insulators because they lack free electrons to conduct electricity. These carbon atoms are strongly bonded in such a way that these form a strong covalent bond, due to which diamond has higher thermal conductivity than any natural material, which is due to the strong covalent bonding and the lattice structuring. So, as there are no free electrons to conduct for the conduction, so the diamonds are excellent electrical insulators. For the self-diffusion in the polycrystalline copper with lattice diffusion coefficient dl and the grain boundary diffusion dEgB and the surface diffusion ds, the correct statement is the correct relation for self-diffusion in a polycrystalline copper is uh, ds is greater than surface diffusion is greater than grain boundary diffusion is greater than lattice diffusion. Let's see each of them. Lattice diffusion is nothing but the movement of atoms within the crystal lattice. Within the crystal lattice, the atoms, whatever are there, will be moving from the one position to and exchange their position between neighboring lattices. In a polycrystalline material, when atoms are arranged in regular crystal lattice, the lattice diffusion can take place through atomic jumps between the lattice. However, compared to the diffusion at grain boundaries or surfaces, this diffusion is very low. Okay. Jumping from this position to this position to other position, it is low. The grain boundary diffusion is nothing but if this is in a polycrystalline material, if this is grain 1 and this is grain 2, the interface between them or the between the two adjacent grains is called as grain boundary. These boundary have different atomic arrangement compared to bulk crystal because if you'll see the atomic arrangement might be like this in grain 1, the atomic arrangement like this in grain 2. When it comes to grain boundaries, due to this differences in atomic arrangement, see, there is a clash between these arrangements. So these interfaces join to form a separate interface again. And here, the atomic arrangements are completely different compared to the bulk crystal lattice, creating defects and discontinuities. So diffusion along the grain boundaries can be more easy compared to the bulk diffusion because they have more spaces also to occupy. And presence of these defects provide more accessible diffusion paths for atoms. As a result, the grain boundary diffusion in a polycrystalline copper is faster than the lattice diffusion. Surface diffusion. If you see, surface diffusion refers to atoms on the movement of atoms on the surface of the material. If this is the surface, the atoms have the broken bonds here. So they'll be having a lot of free energy here, for which the atoms on the surface have very few neighboring atoms compared to those in the bulk. See here, inside the bulk, the atom has all the atoms in the four directions. So for moving of this atom is very difficult. But on the surface, there is only one or two bonds connected, mostly three bonds. So the atoms are very free to move, which allows more frequent atomic jumps and easier diffusion. So surface diffusion generally occurs at faster rate compared to both grain boundary diffusion and lattice diffusion. So the condition for high degree mutual substitutional solid solubility of two metals are the condition for high degree mutual substitutional solid solution solubility of metals are metals have same valency, metals having same crystal structure, metals having atomic size difference of less than 15 percentage, and the electronegativity of atoms should be very close. So metals should have same valency, same crystal structure, should be less than 15%, should not be very large, should be small. Let's see. For the higher degree of mutual substitutional solid solubility, the metal involved should have same valency. Valency refers to number of electrons that can gain or lose when forming a chemical bond. So when the atoms have same valency, it means they have similar electronic configuration, making it easier for them to substitute for each other. And same valency allows for this more seamless exchange of atoms between the crystal structure of metals, leading to higher degree of solid solubility. If metal is having different valencies, it will be more challenging for them for the atoms to replace each other. Metals have same crystal structure. The crystal structure refers to the arrangement of atoms. Uh, so if there is same crystal structure, it is more advantageous. The similar crystal structure ensures that the atomic arrangement is maintained and the spacing is compatible. So when the metal have same crystal structure, their atomic arrangements align more closely and have easier incorporation of atoms without any significant disruptions. So if the metal have different crystal structure, it becomes more challenging for the atoms to jump from one position to other positions and have the solubility will be good. The difference in electronegativity should be small because the if the electronegativity is very large, they will act as more compounds compared to forming a solid solutions. So if the electron activity as low as possible, it would give good mutual substitutional solid solubility. Gallium arsenide, this is a semiconductor. Barium titanate is a piezoelectric material. Iron with 4% silicon is a soft magnetic material. And yttrium, barium, copper oxide is a superconductor. So it is 3, 4, 2, 1. Okay. Let's see each point. The gallium arsenide is a semiconductor. It has unique electrical and optical properties, making it suitable for various electronic devices, transistors, lasers, solar cells. Is widely used in semiconductors. Barium titanate, it's a ferroelectric material that exhibit piezoelectric. Piezoelectric is nothing but it can be used to convert the electrical energy to mechanical energy or mechanical energy to electrical energy. The production of capacitors, transducers, and sensors, due to its ability to convert mechanical stresses into electrical signals, more of barium titanate is used in piezoelectric materials. The iron with 4% silicon is a typical electrical steel known as silicon steel. It possesses lower magnetic losses. So hysteresis losses, it should be as low as possible, because if you'll see historical losses, upon one magnetic cycle, the or the soft steel, whatever the steel or magnetic material, whatever it present, will try to lose its magnetic properties due to eddy current formation on its surfaces. So we need low magnetic losses, high magnetic permeability, making it for transformer or electrical motors or other magnetic applications also. Yttrium, barium, copper oxide, it is a high temperature superconductor. The superconductor properties at relatively high temperature allow development of the superconducting wires, magnets, etc. It's a high temperature superconductor that can exhibit superconductivity at relatively high temperatures also. For the given schematic TTD diagram on the eutectoid steel, the following statement is or are true. The heat treatment 3 leads to the formation of perlite microstructure. Heat treatment 1 leads to the formation of martensite, benite. Okay, let's see the following. Uh, the heat treatment 3, here you're trying to cool the arsenate below the intercritical temperature and then holding the sample, crossing both paralytic start and paralytic finish. So heat 3 will be complete paralyte. So this is true. Heat 1 leads to the formation of martensite. If you say heat 1, you're directly quenching it from A1 temperature to directly below the M90 temperature. The final structure will be martensite. H2, you are cooling it here and then hold it there in a benetic zone, and the benetic region and start and finish both were completed. So it is benite. Leads to the mixture of perlite and benite. H3, as you have already seen, it leads to the formation of perlite. So this is wrong. So the answer is A, B, C. The diffraction pattern of a polycrystalline BCC the is obtained using monochromatic X-rays. Then the X-ray wavelength is given as 0.25 nanometers. If the first peak at Bragg's angle of theta is equal to 30 degrees, then the radius of the metal in nanomaterials. Okay, we know the Bragg's law n lambda equal to 2d sine theta. And the X-rays lambda is given as 0.25 nanometers. Theta is equal to 30 degrees. The radius of the metal in nanometers. So radius is being asked. Okay. So in BCC, we know atom is present at the body center and along the body diagonal root 3a is equal to 4r and the first peak of the Bragg's angle. So in BCC, the first peak occurs at 110. So D is equal to A by root over H square plus K square plus L square. It is equal to A by root 2. So 0.25 is equal to 2 into, so you can write A as 4 into R by root 3 into root 2 sine 30. So if you will calculate the value, so R is equal to 0.25 into root 6 by 8 sine 30. So this is 4. If you'll see, you'll get 0.154 nanometers. The answer is 0.154. The alloy A is cooled slowly from liquid state to just below the eutectic temperature. The ratio of the weight fractions of proeutectide alpha, the weight fractions of proeutectide alpha to eutectic alpha is. Okay. So here, if you'll see, you have using lever rule, you can apply weight fraction of proeutectic alpha is here 15, 30, and 50. So it is 50 minus, oh, sorry. So it is 50 minus 30 by 50 minus 15. So you will get weight fraction of 0.57. Weight fraction of the total alpha is, total alpha if you take 90 minus 30 by 90 minus 15, which is equal to 60 by 75. So the weight fraction of eutectic is total alpha minus proeutectic alpha because weight fraction of proeutectic alpha plus eutectic alpha is the total alpha. So it is 60 by 75 minus 0.573. which is equal to 0.2285. And here it is asked as weight fraction of proeutectic alpha to eutectic alpha. So proeutectic alpha is if 0.57, 0.57 by 0.2285, which is equal to 2.5. Okay, thank you.